Hello. So far, we've been talking about economic problems where you start off with some state variable or state variables, there could be many, and then you face a maximization problem that essentially you're going to repeat tomorrow, except that tomorrow you'll start with whatever state variables you left yourself with when you maximize today. Now, all the problems we looked at so far are deterministic. There is no uncertainty of any kind in these environments. And if you think about macroeconomics and the kinds of things that we'll want to talk about as macroeconomists, that's going to be very restrictive. For example, let's think of a pandemic. Epidemiologists will tell us that a pandemic is the kind of thing that's going to happen at some point, but that still doesn't mean that there is no uncertainty. There is uncertainty about when that might happen. There's uncertainty about the extent of economic or public health damage it would cause, uncertainty about how quickly it would be dealt with, and so on. And we'll want to be able to modify our models so that we are able to talk about uncertainty. And of course, pandemics are just an example. There are all sorts of things that are hard to predict that end up having a macroeconomic impact, whether it's temporary or permanent. So we would like to develop recursive methods that allow us to deal with additional state variables that, rather than being the result of my past choices, are just purely random. Let's have a look at those methods now. Now, let's suppose that the source of randomness in our environment is some variable z. And z could be a number, or it could be a vector. No problem either way. We want something that's going to be changing over time. And normally when we think of random variables, we say that they're drawn from some distribution. Let's call it just f. But here, the things that we are likely to have changing over time won't be drawn from some distribution that is fixed. For example, many random variables that are of interest to economists may depend on their previous realization, in the same way that the capital stock, which is not random, may depend to some extent on yesterday's capital. Yesterday's capital is persistent, and so many macroeconomic variables are likely going to be persistent. So the way we're often going to model this is by focusing on random variables that follow what we're going to call a Markov process. And basically what that comes down to is that zt is drawn from a distribution that depends on the value that variable had yesterday. Of course, at date 0, z0 is given, but z1 will be a random variable that may in principle depend on the value that it had at date 0. Notice, of course, that this, whereas z doesn't depend on what happened yesterday, is just a special case of this. So these are things that we're going to call transition functions. Now let's say that z at all dates is drawn from some set z. And let zeta be a sigma algebra on z. What this means is a group of subsets of this that should include this itself, the empty set. If a set is included here, then its complement is included, and countable unions of sets in this set are also included. Ultimately, what this means is these are the subsets of this space, or this set Z, over which we're going to want to be writing things like probability distributions. These are things that can have weight. They may have zero weight, but they can have weight. And so a transition function, such as f, is a function that maps between the product of z and zeta. What does that mean? It means that they will have one argument that's a value of z and one argument that's one of these sets, which are subsets of this space z, and it's going to map into 0, 1. A way to think about this is as follows. The function f is telling us that for whatever value of z that we start with, it's a z element of the large z set, which corresponds to this argument, f tells us the probability between 0 and 1 that in the next period we will end up in a particular region of z. Remember that zeta is subsets of z, and so it's telling us, give me the value you started with, give me the future value or future set of values that you would like to ask about, and f will tell you the probability that you will end up there. Why all this technicality? Well, suppose z is a finite set. So for example, let's say z is drawn from a finite number of values, z1, z2, up to zn. Then f is easily interpreted as the probability that given you have z t now, you get some zi from this set. This is the set tomorrow. So then this would be the probability of moving from a particular value of z to a particular other value of z. Or more broadly, this could be more than one value. It could be a set, right? And then it's the probability of moving from this particular value to some group of values. In the finite case, it's easy to interpret all of this because you would just add up the probabilities of the individual values if you have more than one value here. The reason for this technicality here is because, of course, sometimes we're going to be drawing z from a continuous space. For example, zt drawn from some interval z between let's say z lower bar and z upper bar. Then you can't really talk about the probability of going from one particular value to another, because of course, if the probability distribution of going to any particular value is continuous, then of course the probability of going to any particular value is 0. And that's why this is defined in this way. It applies to finite sets in a very easy way. It applies to finite sets of possible values in a simple way. But for continuous values, that's why we need to talk about sigma algebras. It's the probability of going from a particular value of z, that's the first one, to some group of values, because any particular future value has a probability 0 of occurring. So that's the reason behind this language. So now that we have this out of the way, let's consider a particular example. Let's consider the basic growth model. Again, without productivity change, just so we can focus on what matters here. And let's suppose that we have everything we had before. You have an agent who is maximizing discounted utility over infinite time consumption. Let's forget labor for now. This is the discount factor. And they're doing it subject to the following. Well, before we had that consumption plus investment must be less than or equal to output, which depends on capital, in addition to capital tomorrow, depending on capital today. The transversality condition. Now let's make things more interesting and say that this also depends on some variable z, and we're going to interpret variable z as productivity. Let's get specific. Before we had the specific production function that we had in mind was this. Now instead, let's enhance it with some factor zt. Now, this environment is not yet specified. Of course, as before, we have k0 given, but we also need to specify one more thing, which is what exactly is the process that this variable z follows. And very often, we're going to use some sort of AR1 process, although there's nothing strictly necessary about that. So let's just say that the natural logarithm of zt plus 1 is equal to rho times the natural logarithm of z plus some epsilon, which is not revealed until the date itself, where epsilon is normally distributed with mean 0 and variance sigma squared. So this is an example of the kind of thing that we're going to be looking at. Before, we would have tried to come up with a recursive representation of this, and we would have started by writing down v of k t. But now we have another state variable that is revealed at the beginning of the period and which is important for decisions. And that, of course, is z. Let's continue here with trying to write down a recursive representation. Apologies for the typos. Yeah, that's what we would do if we were just to try and deal with this analogously. Z is an additional state variable, kind of like k. The difference is that instead of us deciding what its value is going to be tomorrow, it's drawn from some distribution. And what is missing here? What is missing here is, of course, that because z is a random variable, This should be an expectation. Now you should remember from your prior classwork that we can write down the expectation in this form. It's the integral between, in this case, the lower bound of z and the upper bound of z. Of this times, well, times what? If this z is distributed continuously, then you could write it this way. Right? Where f is the probability distribution function that corresponds to big F, where f, of course, is whatever. Before, we would have tried to come up with a recursive representation of this, and we would have started by writing down v of k t. But now we have another state variable that is revealed at the beginning of the period and which is important for decisions. And that, of course, is z. Let's continue here with trying to write down a recursive representation. Apologies for the typos. There. That's what we would do if we were just to try and deal with this analogously. Z is an additional state variable, kind of like k. The difference is that instead of us deciding what its value is going to be tomorrow, it's drawn from some distribution. And what is missing here? What is missing here is, of course, that because z is a random variable, this should be an expectation. Now you should remember from your prior classwork that we can write down the expectation in this form. It's the integral between, in this case, the lower bound of z and the upper bound of z. Of this times, well, times what? If this z is distributed continuously, then you could write it this way. Where f is the probability distribution function that corresponds to big F, where f, of course, is whatever CDF, cumulative distribution function, corresponds to f. F is a cumulative distribution function, since it's the probability of things happening within some range. Now, of course, there may be some CDFs that don't have a PDF. And in addition, there's also the case where Z is finite. And that's why there is an alternative, broader terminology. I'm just going to write it down so you're familiar with it. And that is to write this down in terms of the CDF, is like that. So this terminology has an advantage in that it applies to both the finite and the continuous cases for Z. But again, in any continuous case, you probably have a CDF, so you can think of it this way. In the finite case, well, you could just write it down in terms of the probabilities of moving from one thing to another if you wish. Of course, you might wonder, can we do this? We know we can do this under certain circumstances when there are no random variables. Can we do it when there are random variables? The answer is yes, sometimes we can. We need certain conditions to hold, such as this process shouldn't go off to infinity. Of course, if you look at this, the value of Z is going to be concentrated fairly close to 1 most of the time, and any deviation from that is going to be temporary, as long as we have that rho is inside the unit circle. The idea that this recursive function, or this one for that matter, is meaningful comes down to the question of whether, if we take some function v from the appropriate space and define an operator b of v in the manner in which we did before, does this equation make sense? Or rather, does the contraction mapping theorem apply to this object? And I'm not going to go through all the details, but the broad answer is going to be, as long as this distribution function, this transition function f is well behaved in some ways, which probably means things like it doesn't explode, or maybe it too satisfies something along the lines of discounting, like here. An AR1 process does mean that if you're given your Z, the likelihood of a high Z is higher, but at the same time, there is some rho that's inside the unit circle that makes sure that you don't explode. So this distribution function, these random events are in some sense at least probabilistically contained. Then this B functional, this Bellman operator, is going to be a contraction mapping just as before, and will have a unique fixed point. And that is what's going to make us able to talk about stochastic environments using recursive methods. So, how would we deal with this problem? Well, let's just suppose that our value function is well defined. Then we would need to take these constraints and plug them in as before. Here are the constraints. We can replace investment with this, as we did before. And then we can just subtract capital tomorrow from both sides to leave this. Finally, given that we have local non-satiation of the utility function, we know this has to hold with equality. So we can replace this in here. Then just as before, we proceed to take the first order conditions. With respect to the decision variable, which we've been a bit sloppy about, but at this point it would be capital tomorrow, since you're choosing your investment, and thus how much capital you will have at the next date, given that capital today was given. And of course, the first order condition of all of this with respect to kt plus 1 is going to be minus, and then the derivative of v with respect to its first argument, and all this has to equal 0. With the correct assumptions, such as concavity of u, and f being such that z doesn't explode, this will work. Next, we need the envelope condition, where we derive this by k, its first argument. And of course, k doesn't show up here, so it's gone. So we're going to get u prime here times the derivative of all this stuff with respect to k. That goes away. That goes away. And here we're just left with the marginal product of capital. So finally, we're going to put all of this together to get an Euler equation. Where we're going to replace this derivative with this. And again, since everything here is subscripted by t plus 1, we're going to have to do that here as well. So that's plus 1, that's plus 1, that's plus 1. That, of course, is plus 2, plus 1. This is the expected future marginal product. And that's it. So we still have an Euler equation, except that rather than it linking capital today to capital tomorrow, now it links capital today to capital tomorrow, but also productivity today with expected productivity tomorrow. And of course, since the marginal utility of consumption tomorrow and the marginal product of capital tomorrow depend on that, that's why we have this whole big expectation here. Nonetheless, as I mentioned, as long as this transition function f is well behaved, such as z has a finite set of possible values, or it's such that z can't explode, its expectation is contained and finite for all realizations, then this object will be meaningful and we'll be able to use it in order to characterize and compute equilibria.